Okay, thank you. Yes, Tuomas is actually also here. This is his Master of Science work. I was the thesis supervisor, and so what we were actually studying or... Okay.
Click on the screen.
Yeah, I will go here. So we were actually looking at how we can use the FMI standard to connect these simulation models and run those with our automation system. So there is this FMI standard, and we can share the dynamic simulation models of those physical systems. And this thesis was actually creating the proof of concept, the prototype that we can actually use those standards together with an automation system. So there was the interaction between the automation system and so we were getting the information from the simulation and writing that to automation system and getting the outputs as inputs to simulation model. And so the combination was to use the OPC UA. We could get this bidirectional real-time communication, and actually that was actually very good test. So what is the FMI? So there are over 220 simulation tools, so like MATLAB, Simulink, and you can actually then compile and export the FMU file. So the FMU file is actually a zip file that contains a description, XML, and then the needed libraries to execute the simulation. So there is an interoperability between the simulation tools, and that's also important that you can actually, as with the OPC UA, you can have different programming languages, and with FMI you can have also the different tools to build these FMI models, and then they are tool agnostics. So you can actually get those individual components, a small system like a diesel engine, you can simulate that one, or you can have the stock preparation or headbox or some other bigger subsystem that you want to simulate, or even the whole mill, as we are actually building the simulators for the training. And so what we go through is there are different kind of these simulation models or types, model exchange and the co-simulation. So we can actually run both. So you have the model exchange that you have the FMU contains just the model and the tool contains the solver part. And in co-simulation, you have actually inside the FMU also the solver. And there is the time synchronization, and there is actually now the version 3 coming that you can actually also run the scheduled execution. So that is not all the tools are yet providing that version 3, the scheduled execution. So we were using the version 2 of the FMI. And so this cross tool is good, and then the integration and the reusability is also this portability. And we found out actually during the testing with this was actually part of the virtual sea trial project with Meyeris there and the Kone, Wärtsilä, and Semantum is also there, and we were actually testing the different FMUs and find out that sometimes the FMU doesn't contain all the needed runtime libraries, so there were missing some libraries, and we found out those and solved the problems, and then we got running the different FMUs. And what is the digital twin then? So it's this virtual replica, and we were actually testing a couple of small FMU models to make this the digital twin running, and it's the real world system, and it's the replica of this physical system. So it can used for monitoring, analysis, and optimization. So you can actually use the FMU also to find out before, if you are running it parallel with the real system, you can actually test on the FMU what happens if you change process parameters in different way, and so you can actually see what will happen before you do the change in the real running system. And then how you can actually make this digital twin. It can be used a machine learning model, but that can take how to identify the process parameters can take time. So this physical model is more the mathematical model, and that is mostly used in when we are building those training simulators, because it's fast and easy to, if you know all the process parameters and the physical sizes of the tanks and the pumps and the pipes. Yeah, and this digital twin needs normally the bidirectional communication. And how we were implementing this? So the goal was this build the FMU as a digital twin and have this bidirectional communication. So they were created some FMUs, and then we were using the OPC UA to connect the FMU simulation with our system. And then when the FMU is executing the simulation, then we are actually synchronizing the data between the application and the simulation. And how the system was then actually built up, we have here actually the two servers. Actually, I hope the pointer will work. Yes. So we have the FMU server that actually gets the FMU file and handling it, and then we have the automation system, the OPC UA server there, and then we were using one or two or multiple clients that they are actually connecting those two servers and communicating between those. So this provides the simulation data, and this actually is then executing the applications, and the client is then reading the output, writing there, and reading from here output and writing there to input. So this is both directions updating the data. And how that was actually then implemented. So the FMU server, it will use the methods, server-side methods, so you can actually then import the FMU. It's actually a zip file, so it will get the FMU file, the description XML, and it will actually get into the address space model instance. So this is the model instance, and from the model instance, you can actually instantiate then the digital twin or those instances that will actually execute the simulation. So it will actually get the clone the model here as an instance, and then you can actually create multiple instances that can be executed simultaneously. And in execution phase, you can actually give some parameters that you can control the simulation. And here is actually then the address space. So you can actually see that here is the import model part, and you can import zigzag, that was the test model, FMU model, and you have the connection points there. Then you have some metadata description and the generation tool. You have inputs there, instantiate model license, etc., outputs and parameters and version information. So when you instantiate model, it was the zig1. It contains also the connectors, and then this execute method, inputs, model identifier, model name, outputs, parameters. So it doesn't contain anymore all the not needed metadata. So you can actually then execute this one simulation and give the parameters how you want to execute the simulation. But that's now the basic principle what was implemented in this thesis work. And if we look, this was example how you can change the parameters, so the measurement level was changing. So this is used with the UA Expert, the trending tool. So it was actually also when it builds the instances, it puts there also the in-memory historical access. So it's buffering there into the ring buffer those trend data, historical data. And then this one is now, you connected this with our PID, so you can actually see that the simulation is running, and when you change the set point, it will, our controller will run the PID output and change the values, and then the model behaves quite nicely. And then if you look at the conclusion part, so we can actually use the simulations, and this is the case that the real world data is inputs, and use the simulation inputs and outputs, and so we can actually get this working. And this was actually in virtual C trial. This was target was to use this during the FIT, so we can actually test the ship automation before the ship is built. So that was one target of this work. So we can actually then transfer this data between, and the OPC UA and the FMI standard can actually live together. That was actually also very important for us. So then, if you have questions, Tuomas would come also to the stage or stand up just if you have some detailed questions. And there is also the Tuomas Master of Science work available now from Aalto Publication Archive. Yeah, that's it.